Okay, Bismillahirrahmanirrahim. Welcome back. This is going to be our lecture number 5. Like before going into any detailed tamheed for this lecture, let's get straight to the business. So in this lecture, we are going to complete whatever we were discussing in our last lecture, and that would basically complete our discussion of chapter number 1. So the last topic from chapter number 1, again, it is arithmetic addition and subtraction, and that is going to be done using sine 2's complement. Okay, so sine 2's complement was the technique that we agreed upon last time. We said that we would use it to represent negative numbers or sign numbers in digital systems. Okay, so that is what we said we would use, and here we would demonstrate how we can use sine 2's complement method for arithmetic addition and subtraction. And when we say arithmetic addition and subtraction, we mean the addition and subtraction of signed numbers. Okay, so they can be both positive, both negative, one positive, the other negative, something like that. Okay, the second thing that we'll start discussing is about Boolean algebra and logic gates. This corresponds to chapter number 2 of our book, of our textbook. Okay. Now, some of these things we discussed in one of our previous lectures. So we would basically review that material, and we would go through this material rather quickly, and then we will start discussing Boolean algebra. So Boolean algebra, I hope like you have some introduction to algebra and the rules of algebra. So many of the properties that you will see here for Boolean algebra, you have come across those properties in your elementary algebra courses in your 10th grade and in FSC. So you have talked about these rules and things. We will just repeat them in the case of Boolean algebra, and then we'll also discuss about the standard forms of Boolean functions. So how can Boolean functions be represented in their standard forms? So we'll go into those details. Okay, so let's start. So the first thing that we want to discuss here is sine 2's complement arithmetic. Okay, so how can you add or subtract two signed numbers? If there are two signed numbers, how can we add and subtract them? So we know from our previous discussion that whenever we have a signed number, we will represent that signed number in 2's complement notation. Now, what is 2's complement notation? I hope you remember some of it. 2's complement notation says that if we have a number and that number is a positive number, if you want to represent it in binary, you just convert it into its binary equivalent form. Okay, if that number is a negative number, okay, say for example, we will look at a couple of examples in the next slides. So if that number is a negative number, say for example it is minus 6, and you want to represent it in sine 2's complement notation, so what you need to do is you need to first convert 6 into its equivalent binary. Okay, so first we need to convert 6 into binary, and then we need to take the ones complement of that binary notation. So we'll get the ones complement and then add a 1 with it. Okay, so that then we will get the twos complement notation for 6, and that twos complement notation for 6 would basically represent minus 6. Okay, so that is how we represent sine 2's numbers or sign numbers in sine 2's complement notation. When you're adding such numbers, so the rules for addition are very simple. So what you need to do is you need to add both the numbers, whether they are positive or negative, along with their sign bits. So we know from our previous discussion that the most significant bit represents the sign bit of a number. Okay, whether it is the sign one's complement notation, the sign two's complement notation, or the sign magnitude notation. In all these notations, they have this one thing common, and that is that the most significant bit represents the sign. And we talked about another convention. If the most significant bit or MSB is 0, then the number is a positive number. If it is a 1, then the number is a negative number. So irrespective of what the sign digit is, what the sign bit is, you have to add two sign numbers along with their sign bits. and if there is a carry out of the sign bits, just discard that carry. Okay, now if the sign bits were the same, the numbers that you were trying to add, if their sign bits were the same, if they were both positive, the sign bits would be both 0. If they were both negative, the sign bits would be both ones, and the sign of the result is different, and you add them and then the sign of the result is different, that means that an overflow has occurred. Okay, the result cannot be specified in the set number of bits. For example, if you add two 8-bit numbers, both are positive, and when you add those two 8-bit numbers and the most significant bit of the result turns out to be 1, so when you were adding those two 8-bit numbers, two positive 8-bit numbers, their most significant bits must have been 0, but after addition the most significant bit of the result turned out to be 1. So that means that the result or the sum of the two numbers, the addend and augend, it could not be specified in those in those bits that were reserved for the sum. So that's why the result has overflown into the sign bit. Okay, so this is basically how you do addition. So whenever you are adding two sign numbers, you add them along with their sign bits. If there is a carry out of the sign bit, you just ignore it. You must be careful, like you should pay attention to this thing as well, that if the sign bit of the sum is different from the sign bits of the numbers that you were adding, if the addend and augend had the sign bit 0 and the sum has the sign bit 1, or if the addend and augend had the sign bit 1 and the sum has the sign bit 0, that means the result that you have, it is not correct, the result has overflown. Okay, so now the result that you have, it is not correct, so you need to do something about it. Okay, so the sum cannot be specified in the number of bits reserved for specifying the sum. Okay, so I hope like this is clear to you. We will clarify it further with a couple of examples. Then subtraction. Again, subtraction is the same thing. Like in subtraction, what you do, we have this minuend, which can be a signed number, and we have the subtrahend. We are subtracting the subtrahend from it, which can be a signed number. Okay, so what we need to do is we need to take the complement of the subtrahend, whatever it is. If it is a negative number and we are trying to subtract it, we need to complement it, get the 2's complement of it, and then add it with the minuend. If it is a positive number, but we want to subtract it from the minuend, just complement it, get its 2's complement and add it with the minuend. In either case, whether the subtrahend is positive or negative, if we want to subtract it from the minuend, we need to take its complement. Okay, we need to take its 2's complement and then add it with the minuend, and then follow these rules that we mentioned above. Okay, now let's look at a couple of examples. So we have these four examples here, four possibilities. We are trying to add two positive numbers, a negative and a positive number, a positive and a negative number, and then two negative numbers, and we want to see the result in each case. Okay, I guess here we made a mistake. This is going to be minus 19. Okay, so let's see. So the first combination that we want to look at is, it is plus 6 plus 13. We want to add these two numbers. So plus 6, it is a positive number. In binary, 8-bit binary, this is 8-bit representation of 6. Like if we want to save 6 in a single byte, so what would be the makeup of those 8 bits? So this is how those 8 bits are going to look. 6 is basically 4 plus 2. So this is 4 plus 2. All other powers of 2 are zeros. Okay, so this is 6. 13 is 8 plus 4 plus 1. 8 plus 4 plus 1. This is 13. Okay, rest all the bits are 0. The most significant bit is 0 for both these numbers. That means these are positive numbers. Okay, plus 6 plus 13. Now add these two numbers. 0 plus 1 is 1. This is correct. 1 plus 0 is 1. 1 plus 1 is 2. 2 is 1, 0. So 0 and 1 carry. Okay, so this is a carry. This is not a carry. These two are not carry. Do not confuse it. Okay, so 1 plus 0 plus 1. This is 2, which is 0 and 1 carry. 1 plus 0 plus 0, this is 1. Okay, and all the rest are all zeros. So this is the sum. If you look, the two numbers addend and augend, their most significant bits or sign bits were 0, and the sums sign bit is also 0. They're all the same. So there is no overflow. The result that we have, it is good enough. And what is the result that we have? If you convert it into decimal, it is this is 16, this is 2 18 plus 1 19. Okay, so the result is 19. 6 plus 13 is 19. So it is fine. Now let us look at another scenario. If we want to add minus 6 with 13, what would be the result? Plus 7. How are we going to get this result in binary? So minus 6 is a negative number. It has to be converted into its 2's complement form. How do you convert it into 2's complement form? This is 6. ठीक है. So how do we convert it into 2's complement? First we take the 1's complement. So all zeros are inverted into 1's and all 1's are inverted into zeros. ठीक है. And then we add 1 with it. ठीक है. So what do we get? 1 plus 1, this is 1 0, this is 1 0, and these are all 1's. This is minus 6. This is minus 6. Okay, so this is the proper way of converting 6 into minus 6, taking the 2's complement of 6. This is how we do it. Okay, this is minus 6. You can verify directly if this is minus 6 or not. In 2's complement notation, like the most significant bit's weight, it is going to be considered as a negative weight. So this is minus 128. Okay, this is minus 128. And the rest of these things, they should add to 122 because the final value is minus 6. So this is 64 minus 128 plus 64 plus 32 plus 16. ठीक है, 32 plus 16, ये कितने हो गए? Minus 128 plus 64, this is minus 64 plus 32, minus 32 plus 16, minus 16. ठीक है, plus 8, minus 8 and plus 2, minus 6. ठीक है, so ये साथ में plus 8 हो रहा है और ये plus 2 हो रहा है. This is minus 128, this thing is plus 64, this thing is plus 32, this thing is plus 16. No, sorry, this thing is plus 16, this is plus 8. ठीक है, and this thing here is plus 2. You add all these together, you get minus 6. You get minus 6. So this is minus 6. So you can go directly, इस तरीके से भी आप minus 6 की binary representation मालूम कर सकते हैं. Or you can go this way. Take the binary representation of 6, find its 1's complement by inverting all the bits. 1 को 0, 0 को 1, and then add a 1. So you get its 2's complement, which is minus 6. So this is minus 6. ठीक है. Now add these two together. ठीक है, add these two. So 0 plus 1 is 1. ठीक है, this is fine. 1 plus 0 is 1. 0 plus 1 is 1. अच्छा, 1 plus 1 is 2, which is 1 0. 0 and 1 carry. So 1 is carried here. अच्छा, 1 plus 1 plus 0, 2. 0, 1 carry. 1 plus 1 plus 0, 2. 0, 1 carry. 1 plus 1 plus 0, 2. 0, 1 carry. 1 plus 1 plus 0. ठीक है, and 0, ये क्या होगा? 1 plus 1 2 plus 0 2, which is 1 0, तो 0 और 1 carry. So just ignore the carry out from the sign bit, discard it. We don't need to consider it. This is your sum. ठीक है, this is your sum. And what is the sum? The sum is basically 7. It is a positive number. The most significant bit is 0. It is a positive number. And if you convert it into decimal, this is 7. तो ये क्या है? This is 4 plus 2 plus 1. ठीक है, 4 plus 2 plus 1 is 7. This is 4 plus 2 plus 1, 7. So minus 6 plus 13 should be plus 7. So the answer is correct. Okay. Now let us look at this. The other possibility. We can have a situation where we would like to add plus 6 with minus 13. In this case, the answer would be minus 7. Okay. In this case, the answer would be minus 7. This does not seem correct. ठीक है इसको देखते हैं कि what is the problem with it. So this is not correct. Let us correct it. अच्छा जी. So what is plus 6? Plus 6 is this thing. This binary representation of plus 6 is fine. What is minus 13? So minus 13 की representation ये होनी चाहिए या नहीं? Let's see. ये है plus 13. ठीक है. सो प्लस 13 को कन्वर्ट करें ना जरा माइनस 13 में, तो पहले इसका वंस कॉम्प्लीमेंट ले लेते हैं. सो दिस इज द वंस कॉम्प्लीमेंट ऑफ प्लस 13. 4 zeros will be converted into 4 ones, then 2 ones हैं, तो they will become 2 zeros. Then we will have a 1 and a 0. ठीक है. इन बिट्स को हमने इन्वर्ट कर दिया, इन इन 8 बिट्स को हमने इन्वर्ट कर दिया. सो दिस इज व्हाट वी गेट. फिर इनके साथ हम 1 ऐड कर लेते हैं. ठीक है. So we will have 4 ones, then 0 0 1 1. 4 ones, then 0 0 1. This is minus 13. This is fine. You can verify it other way as well. This is minus 128 plus 64 minus 64 plus 32 minus 32 plus 16 minus 16. ठीक है. यानी ये minus 128 के साथ ये सारी चीज़ें ऐड कर किए जा रहे हैं, तो यहाँ पे हम minus 16 पे पहुँच गए. Minus 16 plus 2 minus 14 plus 1 minus 13. So if you go directly and look at it, so it is fine. This is fine. ठीक है. Now let us add these. I guess this thing is not correct. So 0 plus 1, it is 1. This is fine. 1 plus 1. ठीक है. Now this is not fine. 1 plus 1 is 2. ठीक है. And 2 is 1 0. So this should be 0. ये 0 होना चाहिए. And we should have a carry here. 1 plus 1 plus 0, this is 2, which is 1 0, तो ये 0 होना चाहिए. This is fine. And we should have a carry here. 1 plus 0 plus 0, this is 1. So this should be 1. ये 1 है. ठीक है. Let us make it look like a 1. So this is a 1. This is a 0. अच्छा जी. यहाँ से फिर we don't have any carry. So 0 plus 1 is 1. 0 plus 1 is, this is 1. ठीक है. Rest everything is 1. 0 plus 1 is 1. And 0 plus 1 is 1. So these are all ones. ठीक है. And if these are all ones, then it would be minus 7. ठीक है ना. ये most significant bit is 1. If the most significant is 1, then we can call it a negative number. If it is 0, so ये फिर negative number नहीं है. So the initial answer जो कि यहाँ पे लिखा था, that was not correct. ठीक है. अच्छा, तो अब हमें हमारे पास जो final answer है वो क्या है? 1 1 1 1 and then 1 0 0 1. So what is its value? Is it minus 7? Let's see. So ये है, most significant bit is 1. So it is a negative number, so its weight should be considered as negative. So ये होगा minus 128 plus 64. दोनों को जमा करें, we get minus 64 plus 32 minus 32 plus 16 minus 16 plus 8. So minus 8. Minus 16 plus 8 is minus 8. और उसके साथ फिर plus 1 करें तो minus 7. So now this is minus 7 and this is the correct answer. And now we are fine. ठीक है. अब ये ठीक है. Now let us look at the final situation where we are adding minus 6 and minus 13. So minus 13 की bit representation ठीक है, minus 6 की भी bit representation ठीक है. ठीक है. ये most significant bits भी इनके ones हैं. So everything is fine in order. If we add them, we should get minus 19. We should get minus 19. So the answer that we have, let us verify if it is correct or not. Uska most significant bit is 1. It seems to be correct कि दो negative numbers को हम add कर रहे हैं, so we are getting a negative number. So the answer seems to be correct, but let us verify. 0 plus 1 इनको add करें. 0 plus 1 is 1. 1 plus 1 is 2, which is 1 0 0 1. carry. 1 plus 0, it is 1. 1 plus 0 is 1. 1 plus 1 is 2, which is 1 0 0. 1 carry. 1 plus 1, this is 3, which is 1 1. 1 yahan, 1 carry. This would also be 3. So 1 yahan, 1 carry. This would also be 3. 1 yahan and 1 carry out. So we can discard the carry out, and this is our sum. This is our sum. अच्छा जी. अच्छा, अब क्या करना है? अब देखें कि is it minus 19 or not. So it is easy to verify. Most significant bit is 1. उसका जो weight है that is minus 128. ये 2's complement notation है. So this is minus 128 plus 1 or plus 64. So it would become minus 64. Then plus 32 minus 32. Then plus 8. So 32 or 8 minus 24 minus 20, and then plus 1 minus 19. So this adds up to be minus 19. So this answer is fine. Okay? So this is how you add two signed bit numbers. This is how arithmetic addition takes place. Okay? The addition of signed numbers, whether positive or negative, but if we know कि ये जो numbers हैं ये signed हैं, these are integers, so उनकी addition जो है वो इस तरीके से होती है. ठीक है? You have to convert the negative number into its equivalent 2's complement notation, and then you have to add the 2's complement notation of those numbers together along with the sign bits, and these are the rules that you need to follow. Subtraction is easy. ठीक है? Subtraction is just like addition, but the only thing that you need to do is you need to convert the subtrahend into 2's complement form. ठीक है? उसका 2's complement लेना है, जो भी उसकी bit combination आपके पास है उसका आपने 2's complement लेना है, and then you can add, and just like the way we added these numbers, इसी तरह से addition करनी है. Acha, next we'll talk about Boolean algebra and logic gates. This corresponds to, so chapter number 1 is done. Chapter 1, number 1 of the book is complete. Inshallah, today I will assign you homeworks, a couple of homeworks. एक दो तीन maybe homeworks आपको मैं दूं ताकि आप busy रहें. You'll submit those homeworks when the university reopens. You're not going to submit them online. वो मैं instructions में भी डाल दूंगा. But you have to do those instructions on loose sheets. And when the university reopens, you will submit those instructions. या अगर ऐसा नहीं होता तो you will post those homeworks, क्या कहते हैं, by post. वो आप भिजवाएंगे मुझे, मैं आपको फिर बता दूंगा क्या करना है उसका. But आपने ये by hand करने हैं और on loose sheets करने हैं. ठीक है? और उसको submission का हम बाद में देखेंगे. Acha, so this corresponds to chapter number 2 of our book. The book is Digital Design 4th edition by Morris Mano and Seletti, Michael D. Seletti. Okay, so some of the things we have already discussed as part of our discussion in chapter 1 and as part of the requirement for the first lab that we had. But I will quickly go over that, and then we will zoom in on Boolean algebra. Okay, and we'll spend some time there, and we'll spend some time doing some basic simple proofs. Okay, or looking at proofs. So the advantage of Boolean algebra and all the postulates and theorems that we have in Boolean algebra is that we can simplify expressions for Boolean functions. Boolean functions के जो expressions है ना, उनको simplify करने के लिए we use Boolean algebra, the postulates and theorems, all of it. And what is the advantage of simplification? So the advantage of simplification is that we end up with a very simple logic circuit. हमारे पास जो final logic circuit banega that would implement that Boolean function, that would be a much simpler logic function, and that is the purpose of simplification. Okay, so simplification simplifies the hardware. When you simplify the hardware, you basically save money, the hardware becomes cheaper, you improve its performance, the speed of the hardware increases, and like it's all क्या कहते हैं, it's all a very rosy picture all around. ठीक है, बड़ा आपको अच्छे नताइज मिलते हैं whenever you simplify your hardware. So let's get started. So first of all, binary logic and gates, these terms we went through these terms. Binary variables are variables that take on two values, one of the two values, on and off, true, false, 1, 0. We call them these all these names to those values. But binary variables are variables which take on one of the two possible values. Then we have logical operators. These operators operate on binary values and binary variables. Okay, so they are What are the logical operators that we have? The basic logical operators. These are the AND operator, the OR operator, and the NOT operator. These are the basic logic operators or that we have. Okay? And then we can create more operations using combinations of these basic operations. Okay, so we talked about that earlier as well. So binary variables are variables which take one of two values. Then we have one of two values. So there are two possible values for binary variables. Then we have logical operators or binary operators. These operators operate on binary values and binary variables. Okay, so by definition, that is what they do. They do not operate on real values or real variables. Then we have these three fundamental logic operations, okay, or operators, and, or, and not. You can call them logic functions as well. These are basic fundamental logic functions. Other functions are basically combinations of these basic logic functions. Logic gates are electronic circuits that implement logic functions. Okay, so gates are physical circuits basically, and we know from our previous discussions that these physical circuits or logic gates, as we call them, so in nowadays they are created using transistors. Okay, so they are created using transistors. Transistors are operated as switches, and those combinations of transistors, they are used to create logic gates, and then the logic gates are used to create more complicated circuitry or components that carry out other tasks. Okay. What is Boolean algebra? Boolean algebra is a mathematical system for specifying and transforming logic functions. So we will learn about Boolean algebra. So it is a set of axioms or postulates and theorems, and using those postulates and theorems, we can basically transform logic functions from one form into another, simplify them into a much simpler form, and all that. Okay, so Boolean algebra basically is an algebra for transforming logic functions of binary variables and with these operators. So Boolean algebra is foundational to the design and analysis of digital systems. Okay, so we need to understand it thoroughly, and we need to be able to apply it in order to analyze and design digital systems. Binary variables, we said that they can have two binary values, and these two binary values are called different names. They can be called true or false, on and off, yes or no, 1 and 0, doesn't matter. These are two different values. We can call them any of these combinations of values in different cases. Usually, for the purpose of this course, we use 1 and 0 to denote the two values. Okay, so 1 and 0, we use these values to denote these two values. How do we identify binary variables or Boolean variables? So we can use these letters, capital letters A, B, or small letters X, Y, Z, or letters with subscripts X sub 1, or even words like reset, and these are all in caps. Start it or add one. So when we later on, when we design more complicated combinational or sequential logic circuits, then we use these kinds of identifiers for variables, for binary variables. Logic operations, we know, we talked about this before. There are three fundamental or basic logic operations: and, or, and not. So I hope you remember our discussion about these functions. We look at their behavior in the coming slides. And is denoted by a dot, and is denoted by a dot or the absence of anything. Okay, wherever there is, like, it is not confusing to omit the dot, we can omit the dot. If it can give rise to any confusion, then we may put the dot, but and is denoted by a dot. Okay, so and is just like the symbol for and is just like the symbol for multiplication. Okay, in normal algebra that we have. So at times and is also called a logical product. Okay, it is also called a logical product operation. So AND operation is basically the logical multiplication operation. So it is logical multiplication. It is not a real multiplication. It is logical multiplication. And logical multiplication, like, you should not be confusing it with the normal multiplication. We call it multiplication just because of the symbol that it uses to represent itself. Okay. Otherwise, it isn't multiplication by any means. It is a logical operation. Or is denoted by a plus. Okay, so since or takes the symbol of addition, at times we call it logical addition, though by any means it is not at all addition. It is not addition. Okay, it is a logical operation, logical or. And I hope you remember what this operation is based upon our previous discussion. We will review that discussion as well. So this is called logical addition as well. Not or inversion. Inversion means it makes true false or false true. So it inverts whatever the input is. It is denoted by an overbar. Okay, this is an overbar, or by a quote mark, single quote mark, or by a tilde. So all these symbols can be used to represent the not operation. So these are the fundamental logic operations. We will look at their behavior. This is an example of this notation. Y is equal to a and b. We will read it as y is equal to a and b, not as y is equal to a multiplied b. Similarly, we will read this one as z is equal to x or y. Okay, this is not z is equal to x plus y. And similarly, x is equal to not of a. X is equal to not of a. And again, here we have another disclaimer. These two statements, 1 plus 1 is equal to 2, and 1 or 1 is equal to 1. 1 or 1 is equal to 1. They are not the same. These are two completely different statements. And you should not be confusing these two statements. This is correct because this is a logical statement. Okay, this is a boolean expression or a boolean statement, and this is an arithmetic statement. This is also correct. 1 plus 1 is equal to 2. Okay, in arithmetic 1 plus 1 is never equal to 1. Okay, in boolean algebra 1 or 1 is equal to 1. So this is correct in the context of boolean algebra. This is correct in the context of normal arithmetic. Okay, so I hope you remember these things. We have discussed these things once. Operator definitions. Operations are defined on the value 0 1 for each operator. Okay, so this is the definition of the AND operator, the OR operator, and the NOT operator. And this definition is provided for each value of these are binary operators. All these operators are binary, and OR are binary operators. That means that they have two operands. Okay? And NOT is a unary operator. NOT is a unary operator. So let me represent it as unary, and this is unary. Let me write it completely. This is binary. OR is binary. Let me just represent it by B. And is binary. These are binary operations. Okay? So they have two operands, and the two operands are going to be binary variables, and their possible values are 0 0 0 1 1 0 1 1. Okay? So what is the AND operation? If either of these two variables is 0, if any input is 0, the output is 0. Okay? The output is 0. So any input, if it is 0, the output is 0. The output is only 1 if all the inputs are 1. That is the definition of AND. OR is a binary operator. It has these two binary operands. The possible values for these two binary operands are 0 0 0 1 1 0 1 1. The definition of OR is if any of the inputs is 1, any input. See here, both are ones. The output is 1. The output is 0 only if both the inputs are 0. That is the definition of OR. Okay? And NOT is simply inversion. If the input is 0, you invert it and get a 1. That is what NOT gives you. If the input is 1, when it is inverted, you get a 0. So that is what the definition of NOT is. Okay? So I hope you remember this. Truth tables, we talked about truth tables. So what do truth tables do? So truth tables, it is a table, and it lists all the possible values of a boolean function for all possible combinations of the values on its arguments or inputs. So if we have a boolean variable and it is a function, a boolean function, and it is a function of two variables, so the truth table will list all the possible combinations of those two variables and the value of the function for those two variables. ठीक है, for all possible combinations of two variables. If we have a boolean function that is a function of three variables, for example, if we have a boolean function f and this boolean function is function of three boolean variables x, y, and z. So the truth table for this function would have 8 entries. Why? Because it is a variable of three. It is a function of three variables, and these three variables have a total possible number of combinations. The total possible combinations of these three binary variables is 2 raised to power 3 equal to 8. ठीक है? So for all these possible combinations of these variables x, y, and z, we will the truth table specifies the value of this function. ठीक है? That is the definition of a truth table. So let us look at the truth tables for these basic logic operations. And का truth table ये है. So and is a binary operator. It is a function of two variables. So two binary variables, their possible values are 2 raised to power 2, 4. So these are the possible values that these variables can take: 0, 0, 0, 1, 1, 0, 1, 1. For each possible input combination, the truth table specifies the value of the function. ठीक है? So these are the values of the function for all possible input combinations. Similarly, this is OR. OR के लिए भी हर input combination जो भी possible है उसके लिए आपने उसकी value mention की हुई है. ठीक है? Similarly, NOT के लिए भी वो values हमारे पास given है. So जब आपसे कहा जाए कि किसी boolean function का truth table draw करें, so you have to find out कि वो boolean function कितने boolean variables का function है, फिर उन तमाम boolean variables के तमाम possible combinations आपने draw कर लिखने, list करने, और हर possible combination के लिए output की value या उस function की जो value होगी वो आपने बतानी है. तो that is how you construct a truth table. ठीक है? Truth tables are important. Why? Because they let you know about all the possible combinations of the input variables, and for all those possible combinations of the input variables you list down the value of the boolean function. ठीक है? So truth tables are important in this sense. They are important in this sense. Acha, how are logic functions implemented? Again, we have talked about this. यहाँ पे हम simple show the implementation. I will not spend a lot of time. We have talked about it once, but in actual we do this using gates, and gates are transistors, and those transistors are operated as switches. ठीक है? So you can look कि ये this is OR, पैरेलल में दो switches हैं, एक भी on हो तो light on होगी. So this is how you can implement an OR function using transistors or switches. Similarly, this is an AND, series में दो switches हैं, light तभी on होगी जब दोनों switches on होंगे. ठीक है? And this is NOT. ठीक है? तो normally जब switch closed हो तो हम कहते हैं कि जी it is open. यानी यहाँ we talked about this trick which we use for describing it. ठीक है? So we have already talked about it. I will not spend much time here. This again is a slightly more complicated function than the one that we have. It is a function of switch की state is important in determining कि ये light bulb जलेगा या नहीं जलेगा. ठीक है? तो light कब on होगा? तो लाइट तब ऑन होगा जब हमारा स्विच ए ऑन हो, और स्विच ए के साथ सिर्फ स्विच ए के ऑन होने काफ़ी नहीं है, इन दो में से किसी एक पाथ का एक्टिव होना ज़रूरी है. ठीक है? तो स्विच ए का तो एक्टिव होना ज़रूरी ही है, फिर बीच में जो और दो पाथ्स हैं उनमें से किसी एक का होना ज़रूरी है. तो ए वुड बी एंडेड विद द और ऑफ आइदर ऑफ दीज टू. ठीक है? तो या डी ऑन हो, ठीक है, अगर डी ऑन नहीं है तो फिर ये वाला ऑन हो, यानी बी ऑन हो या सी बार जो है वो ऑन हो. ठीक है? सो इफ दिस इज द केस तब ये लाइट ऑन होगा. दिस इज दिस फंक्शन. नाउ ये इसकी फॉर्म हमें यहाँ से मिलती है, फिर हम इसको सिंप्लीफाई कर सकते हैं और वी कैन क्रिएट अ ट्रूथ टेबल फॉर इट एंड वी कैन डू ऑल दोज थिंग्स. ठीक है. So this is just an example के how you can use these switches to implement a boolean function. So logic gates are basically used for implementing boolean functions, and they are physical electronic circuits. They use transistors. In the earlier days before transistors were invented and transistors were integrated into ICs or integrated circuit chips. So before that, there were vacuum tubes. Vacuum tubes were used kind of as switches, and they replaced those relays which were used before the uh, vacuum tubes. ठीक है. So those things, the relays and vacuum tubes, they all had their own issues. They required a lot of electricity. They were heavy, big and bulky. You could not fit a lot of these relays and vacuum tubes into a small area. ठीक है. So the first electronic computer like ENIAC, it used these relays, ठीक है? Or sorry, I guess it used these vacuum tubes. And the vacuum tubes, yeah, they needed to be warmed up before ENIAC could start working. ENIAC occupied a whole floor. ठीक है, एक यूनिवर्सिटी बिल्डिंग में पूरी एक छत जो है वो घेरती थी. And its computing power was far less than the calculator that you have in your digital watches right now. We are not talking about the your smartphone. Your smartphone is much like a million times faster than ENIAC, और उससे भी शायद ज़्यादा. There is no comparison between the two. लेकिन वो जो छोटे कैलकुलेटर्स नहीं होते जो कि बच्चों को घड़ियों में मिलते हैं, तो उसकी कंप्यूटिंग पावर भी ENIAC से ज़्यादा थी. एंड इफ़ यू लुक एट द स्मॉल साइज और स्मॉल पावर कंजम्पशन, तो आपको अंदाज़ा होता है कि कितनी तरक्की हुई है इन दिस फील्ड, जिसमें वी आर फैब्रिकेटिंग स्मॉलर एंड स्मॉलर transistors. So recently you might have heard about the Apple M1 chip. So the Apple M1 chip is uh, coming into MacBooks. ठीक है. It uses 5 nanometer process technology. इसका मतलब रफ ये है कि ट्रांजिस्टर जो कि एप्पल M1 चिप में बन रहे हैं, तो उनका जो साइज है वो 5 नैनोमीटर के लगभग है. दिस इज वेरी स्मॉल साइज. और उसका फायदा क्या है कि देर आर अराउंड आई गेस 16 बिलियन ट्रांजिस्टर्स इन द एप्पल M1 चिप. 16 बिलियन ट्रांजिस्टर. ठीक है. And what is the area in which these 16 billion transistors might have been fitted? तो ये जो एरिया होगा ना, it would be more or less ये जो मैं यहाँ पे एक्चुअल ड्रॉ कर रहा हूँ रेक्टेंगल, सो इसके एरिया के जितना ही होगा, इससे ज़्यादा नहीं होगा. ये तो स्केल, ये दिस वन इज नॉट अप टू स्केल. दिस इज हियर, दिस इज सपोज टू रिप्रेजेंट अ फ्लोर ऑफ अ बिल्डिंग. ठीक है. सो दिस वुड बी अराउंड से 30 फीट, और ये साइड जो है इसकी 30 फीट होगी, और ये वाली साइड इसकी मे बी 50 फीट या 40 फीट, समथिंग लाइक दैट. ठीक है. सो दिस इज द साइज ऑफ द फर्स्ट इलेक्ट्रॉनिक कंप्यूटर ENIAC. एंड उसकी कंप्यूटिंग पावर और उसमें नंबर ऑफ स्विचेस, यू कैन इमेजिन वो हज़ारों में होंगे शायद. 4,000, 5,000, 10,000, 20,000, समथिंग लाइक दैट स्विचेस की तादाद. यहाँ पे वी हैव 16 बिलियन स्विचेस इन द एप्पल M1, and this is literally this might be its literal size. ठीक है. So it would hardly be around say 5 centimeter by 5 centimeter or something like that. ठीक है. I'm not sure about that, but इससे ज़्यादा नहीं होगा. ठीक है. इतना ही छोटा सा चिप होगा. So this is the magnitude or the scale of progress that has been made in just a span of, this was around 1940s. ठीक है. This was around 1940s, mid 40s, 45, 46, something like that. So it was around that time. And now within the span of say ये 50-70 years, 7 decades, so this is the amount of progress that has been made. Now we can squeeze 16 billion switches into this small area. ठीक है. So I hope ये जो slide है या ये जो चीज़ें हैं, why we mention these things, relays or vacuum tubes, This is because के जो the earlier computers they use those things to implement logic gates and all these functions. Acha, we have also gone through these. This is the symbol of the AND gate. Okay, this is how we show it. This is the symbol of the OR gate. This is the symbol of the NOT gate. And then we talked about the buffer as well. So without this bubble on the other side, so without this bubble, this is the buffer. Okay, so this is the symbol of the buffer. The buffer is transparent. Whatever is at the input, that appears on the output. Okay, so it is not neither complemented nor anything else. It is just it appears in the same way. And we talked about the function or the purpose of buffer in digital circuits. Okay, so you might also need to use issue with that. This is again an example of a truth table for this function. This is a Boolean function. Uh, it is a function of three variables. Okay? It is a function of three variables. So if it is a function of three variables, that means those three variables have 2 raised to power 3, 8 possible combinations. Okay? And those 8 possible combinations are listed here. They are listed here. So 000, 001, 010, 011, 100, 101, 110, and 111. So these are all possible combinations of these three variables. And here again, like इसमें एक चीज़ ये शायद आप नोट कर लें, its value is 0, यानी इसकी जो बाइनरी वैल्यू है या इंडेक्स वैल्यू है ऑफ दिस इनपुट कॉम्बिनेशन इट इज़ 0. ठीक है ना. इसकी इंडेक्स वैल्यू क्या है 001, यानी ये 2 रेज़ टू पावर 0 का वेट है, ये 2 रेज़ टू पावर 1 का वेट है, ये 2 रेज़ टू पावर 2 का वेट है. सो इसकी इंडेक्स वैल्यू या बाइनरी वैल्यू 1 है, इसकी इंडेक्स या बाइनरी वैल्यू 2 है. सिमिलरली नेक्स्ट हमारे पास ये 3 है. ठीक है. नेक्स्ट हमारे पास ये 4 है. ये क्यों मैं आपको बता रहा हूँ, ये इसलिए बता रहा हूँ कि यही बूलियन फंक्शन जो है ना, ये जो ट्रूथ टेबल है, इसको आप किसी और फॉर्म में भी रिप्रेजेंट कर सकेंगे. और वो उस फॉर्म में हम क्या करेंगे, उस फॉर्म में हम बजाय इसके कि ये तमाम जो इनपुट की कॉम्बिनेशंस हैं ये हम नोट लिखें, हम ये जो इनकी इंडेक्स वैल्यूज है ना 0 1 2 3 4 5 6 7 सिर्फ इनको लिखेंगे. ठीक है. और कौन सी इंडेक्स वैल्यूज लिखेंगे, वो वाली इंडेक्स वैल्यूज लिखेंगे जिसके लिए फंक्शन की वैल्यू 1 है. ठीक है. तो दिस वुड बी अनदर फॉर्म ऑफ representing boolean functions. ठीक है. अच्छा जी. So let me चूंकि हम इसकी बात करने लगे हैं, so let us talk about that further. For example, यही boolean function है. So इसको we can represent it as this is x y, ये x y z का function है. ठीक है. अच्छा. So we can represent it as what? As a logical sum of these index terms. कौन सी वाली? 1, ठीक है, 4 and 5 6 7. 5 6 7. ठीक है. अच्छा. So ये जो फंक्शन है boolean function, it can be represented by this truth table. ठीक है. This is one representation. It can be represented by this expression, ये जो लिखी हुई है यहाँ पे, f is equal to x or y prime z. ठीक है. इसका क्या मतलब है कि फंक्शन इज वन इफ x इज वन, तो जहां जहां x वन है तो x यहाँ इन चार कॉम्बिनेशंस के लिए वन है, तो ये तो यहाँ पे वन होगा इन चार के लिए. और कहाँ पे ये वन होगा? यहाँ पे x जीरो है, तो यहाँ पे x जीरो है, तो इसका मतलब ये कि नाउ दिस टर्म बिकम्स इम्पॉर्टेंट. तो और वहाँ पे ये वन होगा जहाँ पे y जीरो हो और z वन हो, तो y जीरो और z वन यहाँ पे है, और बस दैट्स इट. सो एक इस पॉइंट पे ये वन होगा, तो सिर्फ इन 5 पॉइंट्स पे ये वन होगा, बाकी ये जीरो होगा. सो यू कैन स्पेसिफाई इट लाइक दिस कि दिस फंक्शन, this is another specification, another form of specification of this function, कि it would be one at these index terms 1 4 5 6 7. ठीक है. तो इन पे ये वन होगा, बाकियों पे ये जीरो होगा. So this is another form of representation of Boolean functions. अच्छा, we'll talk about this later. ठीक है, बाद में इसका जिक्र आएगा. ये इसका लॉजिक डायग्राम है. अगेन वेरी इजी. So we are basically ORing two terms. ठीक है. So this is our OR gate. ये उसका final output है F, और यहाँ पे क्या OR कर रहे हैं? X OR कर रहे हैं with Y prime. ठीक है. या y ओवर बार. सो y का हम इन्वर्ट कर रहे हैं उसको, और फिर उसको एंड कर रहे हैं विद z. सो इन दोनों के साथ फिर हम उसको और कर रहे हैं. सो वी हैव गॉन थ्रू दिस इज अगेन नथिंग न्यू. Boolean equations, truth tables, and logic diagrams, they describe the same function. So these are representations of the same function. This expression, Boolean expression or equation, this logic diagram, this truth table, एंड दिस एक्सप्रेशन, ये जो हमने लिखा है इस फंक्शन को एज अ समेशन ऑफ दीज, एज अ लॉजिकल सम ऑफ दीज टर्म्स. तो दिस इज अनदर रिप्रेजेंटेशन ऑफ द सेम बूलियन फंक्शन, जिसको मजीद डिटेल में हम देखेंगे. ट्रूथ टेबल्स आर यूनिक, expression and logic diagrams are not. They are always unique because ये जो truth table है ना, this is like the brute force approach to finding out the true representation of a function. ठीक है. यानी इसमें आप तमाम पॉसिबल इनपुट कॉम्बिनेशंस को डाल लेते हैं, तो देयर इज नथिंग, इसके बाद और कोई चीज़ है नहीं इसमें, यानी आप मजीद वेरिएशंस नहीं कर सकते. लॉजिक डायग्राम और बूलियन एक्सप्रेशंस, दे आर नॉट यूनिक. लाइक वी कैन सिंप्लीफाई और वी कैन कॉम्प्लिकेट अ बूलियन एक्सप्रेशन. सो बूलियन एक्सप्रेशन तो इसको इसमें हम चेंजेस कर सकते हैं. ठीक है. तो और लॉजिक डायग्राम जो है वो इसी बूलियन एक्सप्रेशन को फिर इम्प्लीमेंट करता है. तो अगर बूलियन एक्सप्रेशन आपकी चेंज हो जाती है तो लॉजिक डायग्राम भी चेंज हो जाएगा. फिर लॉजिक डायग्राम और चीज़ों पे भी डिपेंड करता है, कौन से लॉजिक ब्लॉक्स को आप यूज़ करें इन ऑर्डर टू इम्प्लीमेंट दिस फंक्शन. सो दीज टू कैन चेंज, दे आर फ्लेक्सिबल. ठीक है. बट ट्रूथ टेबल, इट इज़ यूनिक फॉर एवरी फंक्शन. अच्छा, नेक्स्ट वील टॉक अबाउट बूलियन अलजबरा. इसको हम रिज्यूम करते हैं थोड़ी देर में. आई विल टेक अ स्मॉल ब्रेक. यहाँ पे थोड़ा सा सूप आया हुआ है, तो मैं अगर श्लुप श्लुप करता रहूँ बीच में तो दैट वोंट बी नाइस. सो लेट अस टेक अ ब्रेक, and after that we will resume this our discussion of Boolean algebra. ठीक है.